Here we have a coil connected to a galvanometer. A galvanometer is just an ammeter, it measures current, but it has a zero in the middle so it can measure both positive and negative current. And you can see what happens if we bring a magnet up to that coil. We get a little pulse in one direction. Nothing when the magnet's still, and another little pulse when we go in the opposite direction. So this effect can be enhanced by the use of a core. Now, if we start off with an aluminium core, or aluminum, then we find that actually we get no obvious effect there. No different, really. If we swap that, however, and try an iron core, then we do get an effect. There is a big improvement. Now, electricity is produced by the rotation of a magnet near a coil of wire like this. So as I rotate this magnet, we get current one way followed by current the other way. And we call that AC current. So if we have a generator, then that's really what's happening inside the generator. You're producing AC current. Now, in cordless charging, this changing magnetism is provided by an electromagnet. Okay? So if I just rearrange this slightly, and what I'm going to do now is provide here a changing magnetic field that's going to simulate the rotation of the magnet. So if we pass electricity through this one way, we get a north pole here. When the current reverses, we get a south pole. And that's very much like what I was doing rotating this magnet nearby. And so that's what we're going to do. I'm going to turn this signal generator on. It'll pulse current one way, then the other way, then one way, then the other way. That produces a changing magnetic field, and that passes electricity on to the other side. So that's how we're getting the passing of electricity from one thing to the other. And that's what's happening in cordless charging systems. There's a coil in the pad of the charging system, and there's another coil in the device. And the electricity can pass from one to the other without them being physically connected. It's actually travelling through the magnetic field that's operating in this gap. The effect is strengthened if we link them with an iron core. That improves the amount of magnetism being received by the second coil, and that produces a much stronger effect. What we built here is called a transformer, with primary coils here passing magnetism to secondary coils, and it allows you to do things like convert electricity from a lower voltage to a higher voltage in what we call a step-up transformer, and from a higher voltage to a lower voltage in what we call a step-down transformer. So every power pack you have for charging your phone will have some version of this inside it that steps the mains electricity down to the voltage that the device needs. So a typical cordless charging system would look something like this. This is your device wanting some electricity. This is the charging system, and when you put your device on top of it, the electricity starts to pass. Okay? Now this isn't absolutely necessary. The iron core does improve the system greatly. It does still pass a small amount of electricity without the iron core. It's just a lot better with the iron core. So your system would be some mysterious charging circuit that you can't really see, and you just plonk your device on top of it and it passes electricity across. But we can see here what's going on inside. It's a core with reversing electricity, and that reversing electricity will then produce reversing magnetic field, and that will produce reversing electricity in the second coil, the secondary turns of your own device. And that will pass electricity across, which can then be used to charge your device. Okay?